24 physics problems. That's the name of the playlist, and that's what I'm doing here. I'm picking 24 physics problems in the calc-based introductory physics course and just solving them as a way to kind of give you a refresher for the course. And so it'd be 2-semester course probably. But here we are, we're in chapter 24, electric potential. I'm going to go over the problem, I'm going to talk about the physics, and then we're going to solve the problem. Bonus, 2 ways again. If whenever I have a way to do it with Python as an extra, I'm probably going to do that. So I'm going to do a Python calculation too because I think it's important. And if you don't want to watch that part, just stop it. And that's cool with me. I'll never even know. Okay. So, is that the right chalk? Yep. So the problem is number 23 from Halliday Resnick and Walker, 9th edition, chapter 24, electric potential. We have a line of charge, uniformly charged rod from negative L over 2 to L over 2 in the x direction, and a point P, a distance d above that in the middle. They don't tell you the charge. They say the linear charge density, 3.86 picocoulombs per meter, the length of the rod, 6 meters, and d is 8 centimeters, 6 centimeters. And so the question is, what's the potential with respect to infinity at point P? And then the second part says, what if half is positive and half is negative? So we're going to do those problems. So we're going to talk about electric potential, but we already did. We already did all this stuff. If you go back to the energy on potential energy, we said that if a force, remember we have work done by a force, is the integral from point 1 to point 2 of f dot, I use dr, they use ds, and that's the work done. If that work does not depend on the path, but just the points 1 and 2, then you can call that a potential energy. And so this would be the change in kinetic energy. If I move this term to the other side, it becomes a potential, and the change in potential energy is negative the integral from 1 to 2 of f dot dr. Now, the Coulomb force is conservative. So the Coulomb force looks like this, F1 over 4 pi epsilon naught Q1 Q2 over r squared r hat. It does not depend on the path that you take. You can do the work done is fine. So if you do that and then you find the potential energy of a charge, which I'm not going to write down because you could do it. And so we have the potential energy for a system of charges. So you have to have 2 charges to have that force so you can have a potential energy. Now, suppose I divide by the value of one of those charges, delta U over Q, we call that delta V. And that is electric potential. Why am I writing this down? Because it's right up there. Oh, I erased it. And delta U is electric potential energy. So don't get those two confused. So delta U is in units of joules, and this would be in units of joules per coulomb, or a volt. So volt is a unit for the change in potential. It's a change in potential, okay? Because it comes from this path integral, so you have points 1 and 2, just like all the other potential energies were change in. Now, it's possible to do this for the potential due to a point charge. And we get, if we integrate with respect to infinity, we write this. V as a function of r is 1 over 4 pi epsilon naught q over r. And this is with respect to infinity. So what that means is that it's a change in, but the other end is at r equals infinity, where we set the potential equal to 0. So that just makes things easier. But that's the potential due to a point charge. Now, if you have more than one point charge, just like with the electric field, let's call that Q1, Q2, and I want to find the potential with respect to infinity at that point. V is equal to V1 plus V2. So it obeys the superposition principle. I can find the potential due to this point at that place, the potential at this point due to that place, and then add it up. What's nice here is that we did this with electric fields, and it was right? But here, potential, since it's based on a path integral, is a scalar. Scalar plus scalar equals easy. Vector plus vector, don't confuse that with E1 plus E2, where we had to add them as vectors. Okay? So you may think, why would you ever deal with electric vector fields instead of potential? Well, you get more information too because you get a direction. Now, that's it. So if you have the electric field, I can calculate delta V as negative the integral from 1 to 2 E dot dr, right? So that just divide by the charge. The force divided by the charge gives me E. The potential energy divided by the charge gives me delta V. Okay. Now, you can also go the other way. I can say the electric field in the x direction is negative the change in potential with respect to x. The electric field in the y direction is negative the change in potential with respect to y. Or you could make that as a derivative, and that's fine. That's good. We're good enough. And then so they go through and pick, they show how to find the potential due to a dipole, the potential due to single points. They derive that equation right there. But all that's in the chapter, and I'm just solving. The name of the playlist is 24 problems. It's not 24 lectures, right? I would do that, but I just don't have the time. I'm really trying to get these done because I do have class starting soon, and the semester starts soon, so I want to get as many of these done because then I'll probably just forget about it. Okay, so we're back to this problem. I want to find the potential at point P due to that rod. Let me just redraw it. You know, I like to redraw things. So here's my rod. And here's my point P. And that's the distance. It's right in the middle. That's D. And this is L. The whole thing is L. So this is negative x equal, let's call this the x-axis. And that's the y-axis. So this be x is negative L over 2. And that's L over 2. Now, I can't find the potential due to a rod. I can find the potential due to a point charge. So if I break this into points, dq, I'll write it down here. There's my little point charge dq. And it's located at a generic position x, right? So I can pick any point along my rod and pick out a point, and I call it dq, and it has a position x. And that's the distance d right there. I'll put this over here. If I want my potential due to just that one point, I can call it, with respect to infinity, I can call that dv is 1 over 4 pi epsilon naught dq over r. So I need my r, which is this distance. Well, lo and behold, look what I have right there. I have me a right triangle. So I have this length is x, this length is d. So this side's going to be x squared plus d squared. And that's my r. So now I have dv is 1 over 4 pi epsilon naught dq over the square root of x squared plus d squared. Okay, now I could integrate the left-hand side, but I can't integrate the right-hand side because this stuff is a constant, right? 1 over 4 pi epsilon naught, it's just a constant. And d is a constant. My x value changes. So x is a variable, but my integration variable is dq. So I don't have it all in the same variable to integrate. So we can fix that by saying the charge on this little piece dq divided by its length dx, right? It has a length of dx because it's in the x direction, is equal to the charge on the whole thing, which I'm just going to call q, capital Q, divided by the total length L. And that is lambda. Right, that's the charge per unit length, which they give over here. But I'm just going to write it as q over L. I don't want to use lambda. So if I solve that for dq, I get dq equals q over L dx. And if I put that in up here, I have dv is 1 over 4 pi epsilon naught q over L dx over the square root of x squared plus d squared. Now I can integrate. All that stuff's a constant. Integration variable dx, the only variable I have is x. So it is integratable. So this is going to, if I integrate both sides, I get v is the integral 1 over 4 pi epsilon naught q over L, the integral from negative L over 2 to L over 2 dx over the square root of x squared plus d squared. Now, I like to integrate things, right? But we have a problem. You want to think, first thing you should come into your mind, u substitution. Maybe I could call this the square root of u and then get du up there. But if I do that, I have x squared plus d squared. Du is going to be 2x dx, right? Because I have a power rule. So I don't have an x up here, so that's not going to work. There's some other tricks you could do. Maybe square both sides, get in, separate in the fractions or something. I actually don't know how to do that. So in this case, I'm going to use, this is actually math table book. You can look it up online if you want. I'm not going to judge you. But I like my math table book. I got this in, I remember I got it in like when I was an undergraduate. So I'm on the 28th edition. So this is the CRC math table book. And so what you need to do is to look up in here, find that integral. And I did. It's right, where'd it go? There it is. It's number 157 in my book. Can you see that? Let's see, 157 is right there. So you look up things for containing square root of x squared plus a squared. And so that's what I have. So if I do that, I get the following integral. V is 1 over 4 pi epsilon naught q over L. And then I'm looking at my thing here. I have the natural log. It says log. That's how old it is. The natural log of x plus the square root of x squared plus a squared. But here I don't have a squared, I have d squared. And then I evaluate that from negative L over 2 to L over 2. And that's that. Okay. So, we have this at L over 2, and then we have this at negative L over 2. And I don't like to take the natural log of x, right? That's weird. So instead what I'll do is I'll write this as this at L over 2 divided by that at negative, this minus that, right, at negative L over 2. That'd work, right? I think you could probably do it as, I feel like I'm going to make a mistake here, but I'm going to proceed anyway. I don't normally throw away videos, but sometimes I get so stuck. I'm like, whoop, or I went so wrong. But here we go. V is 1 over 4 pi. Let's say if I had ln of x from negative L over 2 to L over 2, that would be, that's where you can see that. That'd be ln of L over 2 minus ln of negative L over 2. Oh, you can't see that. And then so if I have a subtraction of natural logs, that's the same as division. So it's the ln of L over 2 over negative L over 2. Yeah, so that does work. So let's do the same thing over here. I can say V is 1 over 4 pi epsilon naught q over L. And then I have the natural log. I'm going to put an L over 2 up here. L over 2 plus the square root of L over 2 squared, which is L squared over 4 plus d squared. And then on the bottom, I have negative L over 2 plus the square root of L squared over 4 plus d squared. Because that one's squared, so it doesn't really matter. And so you see the units work out, and it's a good thing. And I think I'm just going to leave it like that. It's a terrible format, but I will leave it like that. Okay. So that's my potential. I can find my charge Q up here by just saying multiplying the constant times L, and I'll do that in a second. And then I have D, and I have, that's it. Yeah, so that's my potential. Now, I'm going to actually I'm going to calculate that numerically in Python. But I want to look at the second part of the problem. The second part of the problem says this. Suppose that this side is plus and this side is negative. And now what happens to the potential right there? And then I want to talk about one other thing too. So if that's the case, I can set up an integral over this side with a charge of positive. And I'm going to get a positive v plus right there. And then I can do the same thing over here and get the potential right there, and I get a v minus, because that's a minus charge. This is going to be a minus potential. That's going to be a positive potential. But due to symmetry, the potential due to the negative side is going to have the same magnitude as the positive side. And since they're scalar quantities and not vectors, then that plus that is going to be equal to 0. So if I make that one negative and that one positive, I get 0. Now, here's a great question. So here's my plus, 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 minus, 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 p, and v is equal to 0 right there at point P. What about the electric field? Is that also equal to 0? And the answer is no, right? Because we're not going to get the exact same calculation. But in general, if I take all this stuff and I find the electric field right there, it's going to be something like this, E plus. And then I do the same thing over here, it's going to be right there, E minus. And you'll notice that those two vectors, even if they have the same magnitude, are not in equal and opposite directions. So when they add together, they're not going to add up to the 0 vector. So you can have a potential of 0 with a non-zero electric field. Very, 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 very possible. Okay, now let's do this numerically. I'm going to do that problem numerically. So I did this with the electric field. What I'm going to do is to break this into n pieces and then just find the potential due to each piece and add it up right there. Pretty easy, right? So each of these pieces will have a charge dq as q over n, and then I'll just need to find the length between pieces, which is a little tricky. It's not going to be perfect, but it'll be fine. So I'll call this dx is going to be L over n, and then I can start right here, and I can move them over to the side. And then I can find all those pieces. Now, if I start in the middle and I move over, I won't have one in the middle. So I'm going to actually put one in the middle. If I break this into, let's say, I'm going to do it like this. So I want to have an odd number of pieces. If you don't, I mean, it'll still work. If you let the thing go to a very large number, it doesn't really matter. I'm going to use the odd number of pieces. Let's jump over to Python, which I didn't pull up a Python thing already, so that's my fault. Let me pull it up real quick, and then I'll switch, new trinket, web v Python. Let's go. Okay. So Python, here we are. Let's just go ahead and enter all our constants and make this bigger. So first thing I'm going to do is to say just this stuff that from the thing. D is 8 centimeters, 0.08. L is that big enough? L is 6 centimeters, 0.06. Lam is this lambda, 3.68 times 10 to the negative. Pico is 10 to the negative. Let's see, is pico 10 to the negative 18? Let's see. Pico meters. 10 to the negative 12. Okay, I don't know why I forgot that. So E negative 12. And then I need K, the Coulomb constant, 9 times 10 to the 9th. So let's find Q. Q is going to be lam times L, and then I have everything in terms of what I want. Now let's break this into 5 pieces. N equals 5. dq is Q over N, and then dx is L over N. I don't know if this is going to work. Okay, RT is vector 0, 0, 0. So that's going to be my starting location. Let's make an observation location too. OBS is vector 0, D, 0. And then I'm going to make a sphere there. It's going to be at position OBS. It's going to have a radius of, let's say, L over 20. Let's just run that. There's my observation location. Just, you don't have to draw that at all. Now I'm going to make a sphere. Oh gosh, let's see. I'm going to make them 2 at a time. Yeah, so I'm going to start in the middle and go outward. No, I'm going to start at RT is negative L over 2. It just makes it less complicated. So I'm going to start on the very left-hand side, and then I'm going to move across. And again, it won't be perfect, but it'll be fine. So while RT dot X is less than L over 2, I'm going to do the following. Make a sphere. So sphere position equals RT, radius equals, let's say, again, L over 20, color equals color.yellow, just so it's different. And then I'm going to move my RT vector. RT equals RT plus vector dx0, 0. And then that should be it. Let's see if that works. There. So there's my point. And you'll notice that it's off-centered a little bit. You see that's a problem, right? Because I started at that and moved over x and x and x. It's going to be a problem if I have a low number of points, but as I increase the number to 5,000, it doesn't matter. So you could fix that if you want to. Not going to fix it. Okay. So now I want to calculate the potential. So I'm going to start off with the potential of equal to 0. So I can add something to it. Now over here, before I move that, I'm going to calculate dV. It's k times dq divided by mag r. But I didn't calculate r. So I need to calculate r as OBS minus RT. Right? So that's the vector from my particular point charge to my observation location. And then I take the magnitude of it because I'm dividing by the magnitude. And then I can add that to my total. V equals V plus dV. And that should be it. Now down here we can print that out. Print V equals V volts. Run it. And I get that 0.024. Okay, let's increase the number to something reasonable, like let's say 500. Now you see it looks a lot better, but I still get about the same thing, so that's pretty good. Now what we need to do is to use our theoretical calculation and see if we get the same thing. And here's where I'm a little scared, but let's just do it. Okay, so I'm going to go down here and call this VT, the theoretical calculation. I'm looking at my equation. I have K times Q over L. Did I call that Q? Yep. And then I need to multiply it by the natural log. I think, yeah, we use log. And then I have the natural log of L over 2 plus the square root of L squared over 4 plus D squared. And then all of that I'm going to divide by this. Copy, divide by, and then it's going to change that to minus. And that's it. And let's see if that works. I'm scared. Okay. Print VT equals VT volts. If it doesn't work, what? It worked. Pretty much the same answer too. Come on, you gotta respect that. So if you didn't stay for the Python part, then you missed out. But if you missed out, you wouldn't even know you missed out because I'm telling you missed out on the part where you missed out on. So I will give you a link to this code down below, and that's the next problem for electric potential. I don't even know what the next chapter is, but I'll get that one out tomorrow or something like that. So that's it. Talk to you guys later.